Hi, welcome to anyone to this new tutorial on Copernicus products. My name is Álvaro de Pascual Collar. I am going to present a Jupyter notebook on a multidisciplinary analysis of the Amazon River plume. This notebook is presented in the framework of the workshop of marine data for South America. So jumping into the home page of the course, here is the homepage of the course. You can access the Jupyter contents by clicking here in this link, Jupyter Notebooks, and here appear a web page where you can see different options like the guidelines to run the notebook and some documentation to download the notebook and run it in your own laptop. And also you have an option for free registration in Copernicus Marine Services. You probably know that to run this tutorial, you will need to be registered in Copernicus Marine Services. So if you are not yet registered in Copernicus Services, please click here in this link and go for registration. And here in the middle, we have the access to the Jupyter Hub platform. Clicking on it, we go to the Jupyter Hub platform, and well, we have to log in the platform using our Copernicus credentials. We enter into the platform, and here we have the Jupyter Lab environment, where we can define two main areas. In the left panel, we have a file browser where we can see different folders and files. The most interesting folder here is this Jupyter Notebooks folder, where if we click on it, we can see that is stored the contents we are going to see today. But it's really important to note that we cannot run the content, the Jupyter Notebook, in this Jupyter Notebooks directory. This Jupyter Notebooks directory is just a storing directory. So first thing we have to do in this tutorial is to copy this Training South America 2024 content into our home directory, which is the directory that appears when we click on this folder here. To do this, we are going to jump into the other area of which is a workspace, clearly, where we can see different buttons to run different notebooks with different Python environments, or also we can open a Linux terminal. So we are going to use Linux to copy this content. Well, this terminal is, as I said, a Linux terminal, so we can use Linux commands, for example, -L, to see the directories and files in the place where we already are. And for example, we can see the directory ll Jupyter Notebooks, and we see the Training South America 2024. So what we need now is to copy this Training South America to our directory, and to do that we are going to use the Linux command copy cp-r, because it has to be recursive, and the source of the copy, for example, is Jupyter Notebooks and Training South America 2024, and the destination of the copy, which is a dot. A dot is a symbol that means the location where we already are. When we run this command, here there should be appear, as you can see here, a new directory that is Training South America 2024, and this directory is under your home directory, right? So now you can access the directory and run the tutorial. We can close this window and run the tutorial by clicking on this file, O1 Notebook Beginner Intermediate. This is the Jupyter Notebook, and for people who is not familiar with this kind of format, I will say that these Jupyter Notebooks are kind of documentation that is formatted in HTML, so it's very similar to the documentation we see in any web page. And inserted in the documentation, we find this kind of cells that contains Python code. This Python code can be run by clicking on this button, the Run button up here. And while we click on this button, we will see here an asterisk that shows that the cell is running. And after running, the cell shows a number that is the identification number of the cell. And well, you can insert here any type of changes in the cell, so you can see the influence of your modifications in the code. And well, this is the format of the tutorial, and the tutorial we have designed it on covering 6 different sections. First of all, it's an introductory section where we will talk about the mouth of the Amazonas River, and after that we will see 4 different exercises covering different Copernicus products, trying to cover the wide spectra of Copernicus products and Copernicus variables to show that Copernicus products can provide a lot of different variables that can be interesting for many different uses. For example, in this tutorial we will learn how to use modeling products from physical modeling data and also biochemical modeling, but also we will learn to use remote sensing data, products produced from satellite, and also we will use observational data took in situ with in situ sensors, right? Well, going to the first section, I will introduce a little bit about the behavior of the Amazon River plume. The Amazon River plume is probably one of the biggest, if not the biggest, plume in all over the world. It behaves following the transportation of the North Brazil current, but after being transported northward by the North Brazil current, it splits in 2 different paths. The main path is the path that follows the North Equatorial Countercurrent, so part of the properties emitted by the river are transported towards the inner ocean. But there is also another path that is produced by the formation of eddies here that are transported parallel to the coast towards the Caribbean Sea. Well, we will see how this image has been created with my ocean view. This is an image of chlorophyll concentration produced by satellite. You can see. This is the product we have used, and we will see that in this tutorial we will also use this kind of product and this kind of variable too. Well, for continuing with the introduction, here there is just some bibliography if you are interested in going further, to get further information about the behavior of the Amazonas plume. And well, we have already run this cell before. This is the setup. The people who is familiar with Python code probably know that the first lines in any Python script are devoted to import all the libraries we will need in our code. And well, we continue with this work flow, and in this cell we just include all the libraries that we are going to use today. I'm not going to spend too much time on this. I just will tell that we are importing some libraries, and also When we import a library, we usually use an alias to call this library. So once we are using functions for example, this datetime library, we will call these functions by dt, right? And here we are using, well, libraries like pandas and datetime are libraries that we usually use for different uses, but in this case, we are going to use them for formatting dates. We will use also NumPy, which is a numerical library to make mathematical computation, and also XRI that is very useful for accessing netcdf files, and matplotlib and cartopy are libraries for plotting functions, with plotting functions to plot maps and to plot scientific diagrams. And here I will stop over this Copernicus Marine client. This is the Copernicus Marine Toolbox. This library is a very interesting library that is being developed by by Copernicus services. This library is the library that we are going to use to access the Copernicus data store and to request data and to download data, the data we will use in our tutorial. Here you have a table with a summary of the libraries we are going to use, and also you have the link to the documentation of any library. If so, you want to get further information about any of them, you can explore everything you need. And obviously there is also the link to the Copernicus Marine Toolbox. This is the documentation of the Copernicus Marine Toolbox, where you can get all the information you need to use this library. But in this tutorial we will see a lot of uses of this library on some exercises and some examples on how to download different types of data. Well, about how to install this Copernicus Marine client, this Copernicus Marine Toolbox in your computer. There is also a Copernicus Help Center that you can use. So you can use, and we recommend to use the installation using Mamba, and here you can download a YML file that you can use to install this Copernicus Marine Toolbox. But in this tutorial we also include this Copernicus Workshop Python environment, which is a YML file with all the configuration you need to run this specific example, right? So you can follow these instructions, but instead of using this YML, Copernicus Marine Environment YML, instead of using this file, please use this other file that includes the installation of different libraries like matplotlib, cartopy, netcdf4, also XRI, etc. Well, we continue with the introduction, and here we present some information about the data sets we are going to use. We will explain these data sets in deeper later, but when we use it in each section. But we will say that, as well, we have this. We are going to use these 5 different data sets. From these data sets, we have 2 data sets that are produced by modeling methods, the analysis, forecast, physical and biochemical modeling. And also we use Ostia data, which are data obtained from satellite. And also we obtain data from C-Color. This is a product, a derived product from satellite observations. So we will get the chlorophyll, information of chlorophyll concentration in the sea surface. And also we will use in situ in situ near real-time observations took from Argo Voice. Right? Here we have another cell code that, well, this is just a quite similar section like the setup, but here we are defining some parameters that we are going to use. Are constant parameters, they won't change along this analysis. So we will define it here in the beginning of the program, and well, by clicking this run button. Here you will see that these parameters are also always related with the definition of the spatial domains, since we are going to plot maps and vertical sections and Hofmöller diagrams. We define geographical domains to plot maps, and also we are defining the limits of the vertical sections we will plot, and also the specific location for the plotting of Hofmöller diagrams. So we won't change this location, but I encourage you to once you have seen this tutorial for first time, you can change here to analyze the Amazon River plume from changing the location of the maps and the sections we are defining here, right? Well, going to the first section, this is the second section. This is the first exercise we are going to do. This is first time we are going to access the data, and we are going to plot and define functions to plot the data. We are going to work with this physical modeling data. The modeling data we are going to use is this. This is the identifier of the product we are going to use. You have also the link here to go to the web page of the documentation for this product, Copernicus product. You can see here. This is a product that is provided in 3 dimensions, so it has information not only in surface, it also has information in 50 vertical levels with a resolution of 112 degrees, and it also provides information of many different physical variables in the ocean, for example, temperature, for example, salinity, current, sea surface height, mixed layer depth, etc. Always physical variables, right? And this provides information from November 2020 up to the present, and not only the present, but also some forecast. It provides few days of forecast. Later we will see this. We come back to the tutorial here. Here I give you the information you need to accessing the data we will need in this exercise. As you can see here, I provide the accessing to 2 different types of data. The Copernicus data product is always the same for both examples, but one of them is focused using the dataset with temperature data, and we are also downloading the dataset with salinity data. Here, for example, if we go to the web page of Analysis and Forecast product, we can click on here to this link to the download data, and we can get the information of this product. For example, you can see here what variable you have available, and also you can define a specific region in the map to download data, etc. And also you can see here that there is many different data sets, and I will say that, for example, the data sets are organized taking in consideration 2 parameters, right? one of the parameters is the variable start. For example, here these are datasets related with currents, salinity, temperature, etc. And also there is the frequency of the data, monthly data, daily means, and 6-hourly means, right? With this with this web page, you probably know that you can download the data you want. For example, you can, by clicking here, you can select the variables you want. For example, if you want to download salinity, this is the data set we are going to work now. There is just one variable, so you can define here the map you need, and the spatial domain you want to download, and also you can define the date range and the depth range, right? So you can download from surface to up to thousands of meters depth, right? Well, this is a way to download the data, Copernicus data, but in this case, in this tutorial, we are going to learn how to use the Copernicus Marine Toolbox to download the data, right? So the Copernicus Marine Toolbox offers a function that is login. This is the first function we have to run always. This is a function that gives you access to the service, logging this machine into the service. So you have just to log in one time in all the session. So we can click the run button here. And then you log in with using your own Copernicus credentials. And your password, and well, you have to accept this. And once you receive this true, you are logged into the system, so you can request all data you need or you want. And well, after this, we are going to use, we have used the login function, and now, as I said before, we use CMT as the alias for the Copernicus Marine Toolbox. So we are accessing a function of Copernicus Marine Toolbox, the function called login, and now we are going to learn how to use the subset function. It's another function of this Copernicus Marine Toolbox to access the data. This is the main function that we will use to access the data, and here you have a cell where you can see how it's this command. This command has different parameters, for example, the dataset ID, minimum latitude, maximum latitude. As you can see, most of the parameters that we give to this function are obvious parameters like minimum latitude, maximum latitude, or start date time, or minimum depth, maximum depth, which are actually the same parameters we are defining in the Copernicus web page, right? You will have to define this window to download, and also the depth to download, and the date range, right? So we do exactly the same, but in just one command. And well, we have to access a specific dataset ID. And which is this dataset ID? Here we are defining in this cell two different datasets to download. In this exercise, we can download the dataset of salinity, which is this dataset. This is the name of the dataset. And also we could download the dataset of temperature that has this name. How can we know this name? Well, this name appear in the web page. You can see here the name of every dataset, all available datasets, and well, you can access these specific datasets. And if you think it's not clear how to configure this subset command, you can also click here in the web page the automate button, and you will see that the Automate button gives you a recommendation of how to download this data you have configured here. So from here, from this, you have some suggestion, and you can change the things you are interested in. For example, you can change the latitudes and the longitudes. Here you can see also we are not expressing latitudes and longitudes as numbers because we have defined these latitudes and longitudes up here in the definition of constant and parameters. For example, lat min, lat max, long min, and long max. Yeah. So we don't need to type here specific numbers. Well, let's run this cell to see what happened. Well, there appear these 3 lines of error. Don't bother with that. They don't have importance. And well, the system asks you for permission to download this data and also gives you information about the size of the file you are going to download. Yes, well, we type yes, enter. And as you can see, the system is really fast. We are downloading almost half gigabyte of data in few seconds already. Since we have this returned, we already have this file in our system. And well, since we have this file in the system, we can go to the data directory and see the file, right? As you can also, I didn't comment it before in the definition of the parameters of subset function that there is also 2 parameters devoted to specify where do we want to store the data file, the resulting data file, and also what name do we want for the data file, right? Output file name and output directory. With this, we can define the directory to store the file and the file name, the name of the file. Well, all the downloaded data sets comes with in netcdf format. The netcdf format is very common to format to store geophysical data like oceanography data or methodology data. Here we are downloading netcdf files, and to open netcdf files, since we have the data, the file of the data in our system, we have to open this file to access the data inside the file. So to do that, we are going to use a function open dataset from the library xarray, and we just have to type this. We are creating a variable that is the name of the file we want to open, and we only have to call this function using the alias of xarray we have defined it. This is the alias we have defined for xarray, xr, and type the name of the function and the name of the data file we are going to open, and this line will print the result ds variable. As you can see, the result of this function will be stored in this variable, in this Python object ds. This is the object we are going to use to access the data through the use of ds object. Well, we can run this cell, and here it is. We have some information of the file we have opened. You can see here, for people who is not familiar with netcdf format, I would say that netcdf files have 3 types of data, 3 types of objects inside, which are the variables, the dimensions and coordinates, and the attributes. The variables are the arrays, multidimensional arrays that stores the data we are downloading. For example, we can see here we have just one variable called SO, and if we click in this little paper, we can get some information which are the attributes associated to this variable. These attributes are always kind of header, kind of information alternative information. For example, it gives you the long name of the variable, so we can know that this variable stores salinity value and the units, and this is practical salinity units, etc. And well, this variable includes 4 different dimensions, and the dimensions here are time, depth, latitude, and longitude. And as you can see, there are 4 dimensions defined in the file: depth, latitude, longitude, and time. And you can see the number of the length of each dimension. We have 28 different values for depth, etc. And we also have the coordinates, which are the special variables, usually one-dimensional variables that includes the information of each variable. For example, if we can click here in the time variable, you can see that, for example, here you have the information. The valid minimum is from December 2023. This variable has been defined here in the definition of constant parameters. Here we have defined the starting period to download data. So our dataset starts in December 2023 and finishes in February 2024. But today, I'll tell you that today is February 19th, but this file finishes in February 28th. This is because this file includes some forecasting data. So here you can see that this file includes some temporal steps that are in the future, that we are here today is February 18th, and we have few days of forecasting data, right? So we can continue with the tutorial and see here there is a cell devoted for people which is not very familiar with accessing .NET-CDF files in Python. Here there is some commands to access, for example, a variable. For example, if you want to access the variable, you will access the DS, the dataset, using the name of the variable like this. And well, you can also access the list of attributes of the variable by, for example, calling this variable latitude in this case, and this calls the list of attributes of the variable. And here you can see how to access a global attribute, that are the attributes associated not to a specific variable but associated to the dataset, and also the specific variable units of a specific the specific attribute units from a specific variable salinity, right? So you can click here and see the result. And for example, in the first case, you can see the variable information, and you will get this and the list of attributes. If you call the list of attributes, you will get a dictionary like this. And when you print the specific attributes, you will get the result of the attribute, that usually is a text or a number, or it depends on the type of attribute, right? Well, once we have opened the dataset, we can start to work with it. For example, here we are going to present how to plot a map of the surface salinity. To make any plot mainly has 2 different steps. The first step consists on selecting the data we want to plot, and the second step is to make the specific plot, right? For example, here since we have a data set that includes many date or includes, you can see here the values of different time, depths, latitudes and longitudes. If we want to plot a map, we will need to get a specific depth and time values, right? Because we cannot plot a map with 3 depths. We need to define the depth of the map we want to plot and the time, the date for the map, right? So this is what are we doing here. We are using a function from XRI, which is the cell function. This cell function allows you to select a specific period in your data set. For example, here we are selecting in the time dimension the specific date we want for our analysis. This date has been defined in the parameters, and also we are defining a specific depth. We are selected 0 meters depth, so this is the surface value, right? And we are going to plot the result of this new variable created using the cell function. We can click here to run the cell. And here you can see that we have the salinity selected, var name. We have selected the salinity by using the name of the variable. You may remember that in the data set, the variable is called salinity, is called SO. So we have selected the variable salinity and selected this specific date and depth. So we get this new variable, the data to map, that has only 2 different dimensions, latitude and longitude. And now, yes, now we can plot a map of this data set, right? So to do that, we have created this function in the next cell. You can see the plot map function it has many different commands, but we have created 4 different sections for these commands, so we think it's easier to understand the function. First lines of the function are devoted to create the figure and the axis of the figure. Since these axes are a map, we have also to include a projection in the creation of the axis. Also here we have some editing basic features, like for example, if we want to add the borders of the countries or etc. For example, to remove the latitude and longitude labels, because or if we want to include coastlines and grid lines, etc. And you can play with this by commenting some line and seeing later the result of commenting some lines in this function. And here are the main commands we are using to plotting the map. We are using the function from matplotlib pcolor to include the color map in the map, and also some editing commands at the end, like the format of the color bar. Let's run this function here and see the result. Here, as you can see, we call this function plot map, which is the function we just defined, including the data we selected before, and well, we also have to include the title of the map, the variable, and etc., and the units for the color bar. And we have these 2 lines are devoted to create these gray lines that will be the lines. And well, with this we are having the map of salinity, surface salinity, and for a specific date in the region, in the vicinity of the Amazon River mouth, right? We can see the forest water accumulated here in this region, and also the transport of forest water that goes following, as we said before, by the currents, the north equatorial countercurrent towards the center of the ocean, right? North Atlantic Ocean. Well, I said before, these two lines are the lines devoted to create this axe here, and also this dotted line, gray dotted line here. These are the locations where we are going to plot now the vertical section and the Hofmöller diagram in the next exercises. So once we have this first map, we can plot a vertical section of the salinity. And to do that, we have to again first we have to select the data we want to plot. Here you can see we are using again the cell function, but we are going to use the cell functions not one but two times. First, we are going to use the cell function to select the specific longitudes we want, because we want a range of longitudes from this beginning longitude up to this finishing longitude, minimum longitude and maximum longitude. These longitudes were defined here in the definition of parameters in the program. Here, up here, seclat and seclong. As you can see, there is a list with two values. So we are defining the specific longitudes and a range of longitudes, and also to a specific latitude and a specific time, using the method nearest, looking for the nearest value of the requested one, right? We can run this cell here, and you can see that we have selected a new data set, which we are called data to section, and it has just two different dimensions, depth and longitude. Since it has depth and longitude dimensions, we can plot it like a vertical section. And as before, we have done almost the same. We have defined a plot section function. This is interesting. We are working with functions because since we are working with functions, you can take these functions and copy this function and put it in your own programs, and this function should work as long as you are preserving the name of longitudes and depths, the dimensions, but it should work, right? So you can include also your little changes here, and the structure of the function is quite similar to the function before. We first create the figure and the axis for our plot. After that, we use two plotting functions. We use a contour f and a contour function. Both of them are functions from Matplotlib. So they are contour functions to produce a contour map, a contour plot with fillet values and also with lines. We will see later the result. And also we have some editing commands at the end of the function, and we just have to call the function using the data we selected just before here. So using this, we get this vertical section where we can analyze the vertical structure of the fresh water emitted by the Amazon River. You can see here there is a tongue of fresh water following produced by the Amazon River. And where are we defining this vertical section? Well, we have defined this vertical section along this line, right? From here to here. So we are studying the vertical section along this line here in the map, right? As we said before, we can change the location of this vertical section to any other latitude, for example. So we can analyze the tank of fresh water at any different latitude and any different date. And also we can also include a different date in the future, because in this data set we have forecasting data, right? And also, after creating this vertical section, we can propose another type of diagram, which is the Hofmöller diagram. You probably know what a Hofmöller is. Hofmöller diagram is a diagram that usually has in the x-axis the time dimension, and also in the vertical axis it can have different dimensions like latitude, longitude, or depth. In this case, we are going to select a Hofmöller diagram to plot the profile of salinity in a specific location, the temporal section. To do that, we use again the cell function, selecting a specific latitude and longitude in a specific point of latitude and longitude. And after selecting this data to Hof values that only has time and depth dimensions, we can propose a new plot Hofmöller function that is creating the Hofmöller, right? So as before, we are including two lines to create the figure and the axis, and a third part of the function is only devoted to format the figure. And also we have a section with, in this case, it has two commands, pcolor mesh and contour, which are functions from matplotlib. And these functions are devoted to make the specific map we can run here. And this is what we obtain. You can see here we have a temporal x-axis that gives us information of December 23, January 24, February 24, and we can see the vertical structure of the salinity along the time in this location, latitude 7, longitude minus 53. And we can see here the variability of the salinity in the surface up to 25 meters. You can see here the variability of salinity, and this is related with the variability of the plume and the movement of the plume. In some periods, the plume affects this point with more intensity than in other periods where the salinity is higher because the plume is affecting other regions, right? It has some spatial variability. Well, with this, we are finishing this first exercise of the tutorial, where we are analyzing the use of data. We have took as example the near real-time physical modeling data. And here I propose you a new exercise, an exercise that I'm not going to spend time on doing this exercise. I propose you to modify the previous code in section to study the temperature field in the vicinity of Amazon River. Here we have give you all the information you need, because first of all you will have to download a new Copernicus dataset that, as you can see here, we have proposed two different datasets, one for salinity and the other one for temperature. So you have to change here the dataset you are requesting by changing this by TMP, and with this, when you run this dataset, you will be downloading first of all, you have to delete the previous dataset you downloaded, and once you accept this charge, and well, you get this new dataset, and when you open this dataset, you will realize that well, you have the same dimensions, but now the variable is different because you have downloaded a new dataset pointing to a different dataset ID, which is a dataset of temperature. So you can continue with this analysis for this chapter, analyzing the vertical structure and the map of temperature using this dataset. By now, we are going to jump into the next exercise that is similar to the one proposed here, but we are changing now to analyze not only the physical variables of the Amazon River mouth. We are going to download biogeochemical modeling data. So we are going to use here, we propose to use here these two datasets. One dataset that includes primary production data, and also the other dataset provides data of turbidity, right? Optics and net primary production. This is the name of the dataset, and also turbidity. Well, and now the code is pretty the same than before. You don't have to make many changes in the code. You can compare this with the exercise before, and you will see that we are calling the subset function from Copernicus Marine Toolbox, and we are downloading this data at requesting data from a specific dataset, which is the interesting dataset we are looking for. So to know this information, you just have to go to the Copernicus webpage, to the Copernicus Marine Data Store, and see the different available datasets, and see the information. And to know this, it's also very interesting to study this user manual, which is the documentation, the official documentation of the product. So in this manual, you can get all the information of the variables, etc., are included on this dataset. So, well, once you have the dataset ID, you can download the data by clicking, by defining the latitude and longitudes, the geographical information, and also the information of the data file and the path where you want to store the data. And you can run the cell by clicking and accept. And as you will see, now we have a new data set called near real-time biological modelization. So we can open again this data set, but now it's almost the same than before. We are opening this data set, but we are opening not the physical data set, but we are going to open the bio file. So we can run this cell, and here we will see that we have again a netcdf file with 4 different dimensions, but it has 2 different variables. This first variable, it contains information of net primary production, expressed as carbon per unit volume in seawater, but we also have information of oxygen here. So we can make the analysis, not only the primary production, but also the information of oxygen concentration associated to the Amazon River. And well, since we have already defined the functions to plot maps and to plot vertical sections and to plot molar diagrams, we do not need to type a lot to plotting functions, to plotting maps. For example, if we want to plot maps of for example, primary production, for example, here, you could also select oxygen, for example. You just have to select, as before, using the cell function, you have to select the the time and depth dimensions. And once you have the time and depth dimensions, you just have to use the plot map function that we defined in the previous exercise to get the map of the net primary production in the vicinity of the Amazon River. Right? We can see here that the Amazon River has important implications in the production, in the primary production here in the vicinity of the mouth. And also we can see how there is a filament that goes northward and left in this area with that it should be probably kind of eddy that doesn't mixes with the environment. And well, we can continue with the analysis doing as before vertical sections that is almost the same than before. We have to use again the cell functions 2 times in the first case. In the first time we are selecting a range of longitudes and in the second time we are selecting the latitude and time dimensions. So this will create a dataset, a variable that only has 2 dimensions that we can plot using again the plot section function that we defined before. And we can see the primary production associated to the Amazon River along this line as before. This is pretty similar actually with the salinity variable, but it has a maximum here in the output of the river, probably associated with the mixing of ocean water and fresh water. And well, we can also see we can also create Hofmöller diagrams of the primary production by selecting the data associated to a specific latitude and a specific longitude by using the cell function with the method nearest. And we can use again this function that we created before. Yeah, so we do not have to type a lot of things. And with this, we can see the variability of the primary production mainly associated to the mixing layer, which is here between 25 meters depth and 15 meters depth. And as you can see, well, this variability has a lot of correlation with the variability we had in the case of salinity. You see, for example, there is a period where the seawater, ocean water, is more relevant here, and in this period we have higher primary production in the depth layer, right? Well, and after this, this is the second example. This is the second exercise we propose here, which is very, very similar, as you can see, to the example of physical modeling data. We just only have to change the data set and the product we are accessing, and we can produce the same plots and the same information, but with obviously different variables. So we can see different variables on different parameters, biogeochemical in this case. In the exercise we propose here for you to solve at your own, we propose to modify this code to access the biochemical modeling data to study the turbidity of the plume of the Amazon River. And to do that, you have, just as before, the same than before. You have to change the data set you are accessing here in the downloading the data. First of all, please remember, you have to delete this file you previously downloaded, and you have to change here turbidity, and with it you are accessing in this dictionary, you are accessing to this dataset, which is the dataset associated with turbidity, and by running this cell, you will get the information of turbidity, and you will be able to run to analyze the turbidity of the plume of the Amazon River, right? While finishing this exercise, we are going to see how can we change our data set, not only to analyze information of modeling data, which is very interesting, but we can also access information of remote sensing data. Here we are proposing to use, for example, these two different data sets. You can see these data sets are not only different in the identifier of the data set, are also stored in different Copernicus products. So in this case, we will have to change both variables. If we want access to one data set or the other, we will have to change not only the data set ID, we will have to change the Copernicus product, but also they have different variables. Here we are using the parameter variables to select the variables we want to download, because here you can, for example, see for example, analyzing chlorophyll. If we want to analyze the chlorophyll of computed or observed chlorophyll, we can see that this data set, which is a plankton, BGC plankton, L4, 4 kilometers, very high resolution. We only have this data set, we can see that there are different data sets, including different resolutions and different temporal frequencies, and also different variables. So you have to go to over the specific data set you are interested in. And also, once you have selected, for example, the data set you want, you will see that there is some different variables. So since we only need the chlorophyll variable, we are going to select the specific variable, right? So here we are using again the subset function to download the data set we are interested in. This is the ocean color chlorophyll, the chlorophyll obtained from the ocean color product. Here we are obtaining chlorophyll concentrations, and almost the same, the configuration of the subset function is almost the same than before, but since we are working now with satellite data, we cannot specify depths for our data because the satellite data only has data in 2 dimensions, right? It only provides information of the ocean surface for many different variables you can see here, and with very high resolution. Well, let's click in the run button to see how it works, and well, it asks as before for permission, and well, we have this new data file SAT near real time, and we can open the SAT near real time using again the open dataset function. And with this we can start to plot data. But the thing is that in this case we do not have information in deeper layers, we only have information in surface. So in this case, we only plot only make plots and diagrams related with surface data. Since we have defined it before how to plot the function plot map, we can use that function here. For example, first of all, we have to select the information, the specific variable and the specific date to plot. And we can use again the plot map function. We defined it before. So with this, we are creating the map of primary production for this specific date along this region. You can see again the area affected by the discharge of the Amazon River, and also the plume transported along the coast towards the northwest, and the filament transported towards the inner ocean. Well, as I said before, we cannot plot information in deeper layers because we do not have information in deeper layers. So this exercise of plotting satellite data finishes here. And well, again, we propose to change the dataset we access to plot different variables. In this case, we are proposing to make a plot of the sea surface temperature in the region, accessing a different dataset. And as before, you will have to change the dataset we are downloading here in the subset function, right? Instead of chlorophylls dataset, you have to download SST and SST dataset and variables. First of all, delete the previous file, and you can run the solve and accept the downloading, and you get it. Now you can continue with the exercise, but doing the same analysis, but for the variable analyzed SST. Let's plot them up. You can see here we have to select the data for the variable, but since we do not have chlorophyll variable in this case, we must change this variable var name, and attack, we have to define the name of the variable that is included in our dataset, with the name of the variable we want to plot. And after that, we can plot the sea surface temperature in the region for 19th February, right? This is the surface temperature field. Well, and in the last exercise we want to present you, it's an exercise where we are going over observational in situ data. There are a lot of sensors that are getting in situ information, and they are also available through the Copernicus services. To define how to download this dataset is not as easy as before, because we cannot use the subset function, because this data is not aggregated data. It's our dataset that are provided in specific locations. So you will need to use a different function, a different Copernicus Marine Toolbox function, that is the get function. And this, for this, you will need the name of the file you want to download. How would you get this name file? It's difficult to know, right? As before, you need this dataset ID, which is not very clear, and also you need the information of the file. Well, there is a very interesting web page, which is this, the the in situ tag dashboard web page. In this web page, you can navigate through all data are available in situ data available. So you can go to the region you are interested in. Oops. And you can try to filter the information. For example, you can filter information that stations that has information for the last 5 years. And also you can also filter the information depending on the platform, type of platform. For example, we are going to select these platforms, data gauges, river flows, etc. And here you have a clear view of the information that is available for different sensors and different periods. Obviously, these are sensors that usually are not static sensors. They are moving sensors. For example, we can look at this station. We can see this is a profiling float, vertical profiler, that gives information of vertical profiles of temperature and salinity. And it has information from this period of time. And this is the Copernicus product, and this is the data set you need from Copernicus product. And well, how to know? But we said that we will need this file name. How can we get this file name? Well, you can go here in download. Well, you have to obviously authenticate using your Copernicus credentials. And here in download, you get information of the files you can download. Files that has information of the last 30 days or 5 last years of data on all data. We are going to download the file that includes the historical file. So we can get this information and put it here. Just remember this asterisk is important, and you can run the function, the cell, and with this you will download a new data set that has it can take a few seconds again. You are accessing the specific file. As you can see here, commands observation near real time, commands observations near real time profilers. And here there is some lines devoted to change, because since we are downloading a data set or a data set with a specific file name, we cannot define here the final file name. So we are included these 2 lines to define a destination, path and a file name, and we are moving, renaming the downloaded data, renaming this data using this destination variable, right? Well, again, we can open this data file, and here we see some differences. First of all, we only have 2 different dimensions, time and depth. And regarding the variables, we have lots of variables, but inside the depth variables we are downloading, we can see the temperature. You can see here, sea temperature, and also a salinity variable. And there is also many different variables, like for example this QC, that are variables related to quality control. Quality flag is the quality control of the variable, because since this is observational data, we also provide information of the quality of the data, because well, there can have some problems of on the record of the station. So here we have many different variables, not only the variable of temperature, but also have different adjusted variables of temperature. As I said before, this station we have downloaded is a drifting buoy. So since it is a drifting buoy, it's a station that it is not static in a specific place. It is drifting with the currents and etc. So first of all, we can try to do is to plot the trajectory of the buoy. To do that, first of all, we have to run this function. This is a specific function since this is a formatting function to transform the date time 64 objects of the time variable. You can see the time variable is formatted as date time 64. Well, in our plot function, we will use the plot and the scatter functions from matplotlib. So these functions cannot work with date time objects, and so we will have to transform these daytime objects to Gregorian ordinal dates. So this is what it does, this function. And this creates a new variable that is called dates ordinal. Right? And we have defined it since we do not have to already defined a function to plot trajectories. We have already created this code that since it is the first time and we are just going to use it for one time, this is a code we are created to plot the trajectories. Here we are using, as you can see, the scatter function to plot these dots, these colored dots, and the color of the dots are associated to the dates of the data set. So we can see the trajectory of the drifting buoy, and also see the dates where it was in these periods, the dates, the location at any time, right? And to finish in this tutorial, we can plot a Hofmöller diagram of this buoy. This time we also have the plot Hofmöller function already defined, so we can run directly this function, so we can get a Hofmöller diagram, but we have to be careful because this is a Hofmöller, but we have to take in consideration before interpreting this result that this Hofmöller is computed also not only in time, but also the location of the buoy is changing in time, right? So this variability is associated not only to the temporal variability, but also to the spatial variability of the trajectory of the buoy, right? Well, this is the finishing of the tutorial. We also have to propose an exercise where you can change the code here before in this section to analyze the salinity of the measured by the buoy. Well, in this tutorial, we have seen mainly how to download many different Copernicus products and how to access many different variables, and we have learned, we have provided some information about how to plot maps, how to plot vertical section, and how to plot Hofmöller diagrams with Python with Python. And well, to finish the tutorial, I would like to propose this final exercise. I think it's quite difficult exercise because you have to change quite a lot of things. We propose to make the necessary modifications in this code to make the same analysis we have done for the Amazonas River, but focusing our attention in the Mississippi River. Here we propose spatial domain to use. However, you can use any spatial domain you want. Actually, you can transfer this since we are working with global data sets. You can transfer this example to any location in the world or to any river in the world to see how the river, the plume of the river affects the oceanography of the region. And well, this is all for today. I hope you enjoyed this tutorial and you find it very useful.